Hello everyone, this is separation processes course. In this video we are going to discuss the last type of the liquid extraction processes, which is the countercurrent multi-stage liquid extraction. The third type, which is the mm, let me say most famous type of liquid extraction process, which is counter countercurrent multi-stage liquid extraction. So we are still talking about liquid extraction, and we are still talking about multi-stage where we have more than one stage. And now we are going to talk about countercurrent. What's the meaning of countercurrent? Countercurrent, in simple words, countercurrent means opposite directions. One is flowing in this direction, the other is flowing on the other direction. This is countercurrent flow. How it is related to liquid extraction and multi-stage process, that's what we are going to see. Okay. So we have uh, suppose we are interested to determine the number of stages the number of stages required for specific liquid extraction process by a countercurrent process. So now it is like the Make-up-Delay method or Ponchon-Savarite method, where we use this method in order to determine the number of stages required in distillation. But now we are going to determine the number of stages required in liquid extraction process, specifically the countercurrent multi-stage liquid extraction. So how we are going to do this? Uh, First, we need to draw the process of countercurrent multi-stage liquid extraction. Again, we don't know how many stages, so let's say we have n stages. So it is like this, where you have here stage 1, then stage 2, then blah blah blah, I don't know how many stages, up to stage n. Okay. So what we do in countercurrent, we do not enter the feed and solvent from the same side. No, we enter the feed from one side and the solvent from the opposite side, because it is countercurrent. How is this? It is like we enter the feed to stage 1. This is the feed with a composition XF, and then we enter solvent from the opposite side. So this is the solvent and this is X solvent. Okay. Then what we gonna get, this feed, as it moves from stage to stage, it's gonna be a raffinate at the end of the day. It's gonna be a raffinate with XR. But as we agreed, the output from a given stage is gonna hold its number. So this gonna be Rn, refers to stage n, and this gonna be XRn, refers to stage n. Okay? Again, the solvent, as it moves from stage n to stage 1, it's gonna take the solute and leave as extract here. Leave as extract with XE. Again, this is the output of stage 1, so we're gonna call it E1 and XE1. Okay. Then, suppose we are interested in finding the difference between the feed and E1. This difference is gonna be equal to, because we have a continuous process, steady state, no accumulation. So this difference is gonna be same as the difference between is gonna be same as difference between the raffinate and the solvent, Rn minus S. And this we can call this constant difference between the feed and extract, or whatever, Rn and S. This we can call it the difference point. The difference point. So we can call this the difference point, and it has the following symbol: delta R. Delta R. So this delta R, we call this the difference point. Okay. So how to solve a problem in this situation where we want to determine the number of stages? What we do, first, we can write the material balance, because we will benefit from this material balance. And since we don't know how many stages we have, so it's like this: the output of the first stage is gonna go to the second stage, and also the output of the second stage is gonna go back to the first stage, and so on. Okay. So what do? We can make a material balance on the overall system. So a simple material balance is gonna say that F plus S is equal to a mixture is equal to E1 plus Rn. Remember, we are doing it on the overall system. Okay? And similarly, for the component material balance, it's gonna be XFF plus XSS equal to XMM equal to XE1 E1 plus XR1 XRN Rn. So this is a material balance on the overall system. Okay. Okay. Then what do? We do the same thing. We draw the upright triangle and equilibrium curve, and also we draw the phase diagram. Okay. Again, I'm going to focus only on this part, because this is easy to do, as we discussed before. Okay. So I'm going to zoom on this graph and imagine, and now we have this graph somewhere beside it. So let me draw it again. So we would have this upright triangle. Okay, and again, this is the carrier, this is the solvent, and this is the solute. Okay, and imagine we have, let me do it in a better way. Okay, let me do it like that. Yeah, and imagine, or let me do it, why not? No need for imagination. So let's say we have, this is our phase diagram. Okay, then we draw the extract line and the raffinate line. It will be something like this. Okay, then what do? And remember, we want what? We want to determine number of stages. Okay, then what to do? We start by determining our xf and xs. Suppose your sorry, I forgot to write. This is the carrier. This is the solvent, and this is solute. Okay. So again, we start by determining our xf. Suppose our xf is somewhere here. This is xf. And suppose our xs is here. So this is xs. Then what you do again, you draw a straight line between xf and xs. Then you go back to the material balance. We know fs, we can get m. Okay? Once we get m, we know fs and we know xs, xf, so we can get xm. Then we go to the diagram and determine where is xm. Suppose xm is somewhere here, so you draw a horizontal line, and where it intersects the purple line, this gonna be your xm. This gonna be your mixing point. So it is somewhere here. This is your M point. And for counter current multi-stage liquid extraction, we're gonna have only one mixing point. Only one mixing point. Okay. Then, what to do? Since this is a design problem, why it is a design problem? Because we want to get a number of stages. So you need to have a performance parameter. And one of these performance parameters is either xe1 or xrn. You need to have one of these known in order to determine the number of stages. So this is a design problem. Okay. So suppose you know your xrn, you know your performance, and you want to determine the number of stages required to achieve that performance. Then what to do? You locate your xrn, and remember xrn is gonna be on the raffinate curve. xrn is gonna be on the raffinate curve, this curve. Okay? So suppose your xrn is somewhere here, so you draw it. You draw this point. So this point represents your xrn. Then what to do? You connect your xrn point with mixing point. You connect xrn point with the mixing point. Okay? So you connect them. Until you hit the extract curve. Once you hit the extract curve, this gonna be your xe1. This gonna be your xe1. Okay, so this point here is xe1. This is xe1. xe1. Okay, then what to do? Now, the next step is you need to extend the line. You need to, let me draw it, and okay. Let me do it in this color. Okay. So what you do, you look at you look at your xe1 point that you have just determined and your feed point, and draw a line between these two. Draw a line. Then what you do also, you look at your xs point and your xrn point. Okay, and then what to do, you draw a line between these 2 points. Then you have 2 lines. The intersection between these 2 lines is gonna be your delta r, the difference point. It's gonna be the difference point. Okay, so let's see, where's our feed point? Our feed point is here. Where's our xe1 point? It's there. Then we draw a line between these 2 points, extend it. Similarly, you look at where's your xs point? It is here. And where is your xrn point? It is there. Then you draw a line between these 2 points. The intersection between these 2 curves, which is here, somewhere here, this is the intersection, somewhere here. Okay? So this intersection here is gonna be your difference point, gonna be your delta r. Okay? Now, the question here is, what's the benefit of this delta r? The benefit is like this. See, the method tells you that first you start by your xe1 point, then you draw a tie line, so you move horizontally until you hit equilibrium curve, move vertically, then you go back. Okay, so suppose you do this, then you have, this is the starting point, the final point, you connect a tie line, right, exactly as we did before for single stage. So this your tie line. So let's draw tie lines in dark. The dark curve means a tie line. Tie line. Okay? Then you stop here. Okay, you stop here. Then what to do? You you connect this point that you stop at it with the delta r point. Okay, so this point you stop here. What you do, you connect it with delta r point. Okay, you connect it with delta r point. Let me draw it, and no, I think, let me draw it in red. Okay, so you draw this, connect with L, no, it's not like this, connect with delta R point. Okay, طبعا should be straight line. Okay, then the intersection with the extract curve is gonna be your starting point for the next tie line. So this point is the starting point for the next tie line, which is the intersection with extract curve. Okay, so suppose it is somewhere here, then what you do, again, you draw the second tie line, you move horizontally, should be straight line, you move horizontally, then vertically, then go back, then you draw a tie line. Yeah, then you draw a tie line between the initial point and final point. Okay, so it would be something like this. Okay, so this is gonna be your second tie line, and then again you do the same thing, connect this point with delta R point. Okay, then you draw a tie line until. But where to stop? When to stop? You stop when you reach your XR endpoint. Your XR endpoint, the initial point that you draw before. Once you reach it, you stop. Then the question here, how to get number of stages? How to get a number of stages? Simply, number of stages is equal to number of tie lines. The number of tie lines that you draw. Okay? So you start counting. So I prefer to draw a tie line in different color. For example, here I draw tie line in the dark color. So you count the number of tie lines. 1, 2, 3, whatever. The number of tie lines is gonna be your number of stages. And that's it. Doing this, you can get a number of stages. And you can solve the problem. One last thing that I would like to mention here is remember in distillation, sometimes we don't have the reflux directly. We have we have the reflux as function of R minimum. So we need to get R minimum first in order to get a reflux. Same idea here. Sometimes in extraction problems in general, you don't have the solvent directly. The solvent flow rate as function of S minimum, the minimum solvent flow rate. So you need to get, so it could be something like this. For example, S is equal to 1.2 S minimum. So you need to get S minimum first in order to get the solvent flow rate. Okay, so the question here, how to determine the S minimum for counter current multi-stage liquid extraction. How to do this? Simply, you need again to have the two diagrams, the components diagram and phase diagram. You need to have these two diagrams and plot the given data. Okay, so this is carrier, this is solvent, and this is solute, and again this is this is XR and this is XE. Okay. Then what do you do? First you specify where's your XF and XS, same as all previous problems. So suppose your XF is somewhere here, and suppose XS is there. Then what you do, you connect a line between these two. Connect a line between this XF and XS. Okay, and again you need to have your X on N because it's a design problem. So let's say X on N is somewhere here. Let's say XRN on the raffinate curve is here. This is XRN. Okay. Then what do you do? What do you do? Remember, our target is to determine the minimum solvent flow rate. We want to get S minimum. Okay. Okay. Then we want to find a tie line. We want to find a tie line, okay, in such a way that this tie line, if you extend the curve, it will intersect the feed point. How this? Okay, to understand this, okay, so let me do it in a different way to be more clear. Okay, let me draw it like this. Okay. Okay. So what I will do, let's say let's say your feed point is somewhere here. For example, this is your feed point. Then you locate your XS point to be somewhere there. Then you connect the 2 points, XF or XS. Okay? Then how to get the S minimum? First, to get S minimum, keep in your mind this relation. F plus S is equal to M, and XF F plus XSS is equal to XM M. Keep in your mind these relations from the material balance. Okay? Then remember, you want S minimum. So you need to get M minimum first. And okay, how to get this M minimum? To get this M minimum, you need to get XM minimum. Okay, so in other words, you need to get XM minimum somehow. Why? In order to have two unknowns, which are S minimum and M minimum. Again, this is S minimum and M minimum. You have two unknowns, S minimum and M minimum, and you have two equations. You can solve them simultaneously in order to get S minimum. Okay, so the idea here is how to get this XM minimum. This is the idea. It is all about getting the XM minimum. Okay, how to get this XM minimum? That's what I'm going to do. Remember, this is a design problem, so you need to have the XRN. Okay, so suppose your XRN is somewhere here. This is this is your XRN. Then how to get the XM minimum? To do this, it's a trial and error. So you need to start at any point from the extract curve, from this extract curve. Start at any point, for example at this point, then draw a tie line. So you move again horizontally up to intersect the equilibrium curve, vertically up to 45-degree line, horizontally go back to roughen it curve, then you draw your tie line. From initial point and final point. So this is your tie line. Okay, then what you can notice is that this tie line, if it is extended, suppose you extend it like this. This is your tie line. Suppose you extend it. Now you ask yourself, is this extended line intersect with the feed point or not? If it is not, then try another trial, use another iteration. Okay, use another iteration. So let's say this is the second iteration. So let's say we are going to choose a tie line that starts from here. Then what you do, you move horizontally until you intersect there, you move vertically, then you move horizontally, then you draw the tie line between initial point and final point. Okay, so we draw this tie line. Now you ask yourself, if I extend this tie line, am I going to intersect the feed point or not? Let's see. Let's extend this tie line. Extend it. Yeah, see? See? We intersect the feed point if we extend this tie line. So this is our target tie line. This is our target tie line. This is the tie line that we want. This is the tie line that we want. Okay? Then what to do? You look at the intersect between this tie line and the line that you originally drew between the feed point and XS. Maybe because I'm not drawing it to scale, I'm not using a scale here, that's why they are not intersect, but they're supposed to intersect. So because again I am not drawing it to scale, to exact scale. So suppose they intersect, just I need to illustrate the concept. Suppose they are intersect like this, and suppose the feed point is here, your XF. So the line between XF and XS is like this. Okay, so again, because I'm not drawing it to exact scale, that's why they did not intersect. But if you draw to exact scale using a graph paper, this will intersect. So suppose they intersect at this point. So from this point you can read the XM minimum, our target. You can read this XM minimum. The intersection here, you move horizontally and read from the y-axis the XM minimum. The XM minimum. Okay, then you take this XM minimum and plug it in these two equations and solve them simultaneously in order to get S minimum, the minimum solvent flow rate, which is our target. Okay, then once you get the S minimum, you can use whatever relation, S as function of S minimum. Then you can use the given relation in order to get the solvent flow rate. Once you get the solvent flow rate, then you can start the solution and get the number of stages as we discussed before. And that's it. That's all for this counter current multi-stage liquid-liquid extraction. Thank you for your listening. I wish you all the best.